All right, everyone, we'll begin with today's lecture. So before I started with the lecture, I wanted to just put up a new handout 0 that Professor Shenoy has uploaded to Canvas. A reminder that homework number 3 is due next class, and we'll be giving out homework 4 then as well. And there's a little typo here. Homework 4 will cover up to handout 12, which will be OK because homework 4 is due Friday, February 26th. We'll finish handout 12 next week. And so there will be a week between finishing the material versus doing the homework. We've also confirmed all of our guest speakers, and they're listed here. And so Jamie Henderson is a neurosurgeon here at Stanford. He'll be talking about deep brain stimulation. E.J. Chichelinski is a professor here, also of neurosurgery. He'll be talking about retinal prostheses for restoring vision. And then finally, we'll have Professor Flip Sabes from UC San Francisco. He'll be talking about writing in information into the brain, which, based off of several discussions I've had with you guys, have had with you all, is of interest. Yes, Nathan?
Has anything schedule-wise changed, or is it just info on the speakers?
Just info on the speakers. Yeah. There have been a few other minor changes, like the content of handout 12, but you guys will see that as we go through it. Due dates are all the same. All right. So where we left off on last Friday, Professor Shenoy was going over the population vector decoder. And you guys remember it had this really simple form where your decoded velocity, xk hat, was proportional to some sum over all of your neurons of each neuron's firing rate at time k. That's a little k right here, times its preferred direction. And this was a very simple and intuitive decoder, right? We thought of this as just the vector sum of each neuron's preferred direction. And so if we have here x velocity and y velocity, we could say neuron 1, for example, votes for a velocity in this direction. Neuron 2 might vote for a velocity in this direction. Neuron 3 might vote for a velocity in this direction. And maybe neuron 4 votes for a velocity in this direction. And so each of these vectors here correspond to this y times di, where di is just the vector direction, the unit vector direction, and yk of I is the magnitude of that vector. And so we sum all these vectors, so we just sum them head to tail, and we might get a velocity that looks something like this. And so this is exactly what Professor Shenoy went over last Friday, and it seems very intuitive based off of what we've learned so far regarding the motor system, regarding how tuning curves can model to an extent the neural activity. But there are several intuitive things about this decoder which are missing. And so one is that we see that the kinematics at time k are a function only of the neural data at time k. But what about the neural data at time k minus 1, or the neural data at time k minus 2? And so here, the differences between the k's are our bin width, right? So for example, let's just say the bin width is 20 milliseconds. And so we're saying that the decoded kinematics at time 500 milliseconds are a function of your neural data at time 500 milliseconds. But what about the neural data at 480 and at 460? And we know from observations that this neural data is, in fact, informative of the velocities. And that sort of makes sense. When you're making a reach, it takes maybe a second to make that reach. And over that reach, if you're going at, for example, 10 centimeters per second at the middle of the reach, 20 milliseconds later, you're probably going at a very similar velocity. And so both the neural data and the kinematics are correlated across time. And so how can we use spiking history to improve this decoder? Another thing that we might want to incorporate into these decoders are things that we know either about the robotic arm we're controlling, for example, what are those arms' dynamics, or maybe even things about the computer cursor that we're controlling. So for a computer cursor, we know that there's generally inertia. And what do we mean by that? Well, let's say at time 500 milliseconds, the cursor, the computer cursor on the screen, is moving to the right at 50 centimeters per second. Well, there's a pretty good chance, like we just said, that at 520 milliseconds, the decoder is still moving to the right, and the velocity isn't very different. Maybe it's 40 centimeters per second. So how do we encode things like this into our decoder? Because right now, with the population vector, decoding just on the neural data at time k, we know that this neural data is noisy, and so there's very well the opportunity, or there's very well the chance that between 500 milliseconds and 520 milliseconds, the population vector might actually decode a leftward velocity in the adjacent time bin at 10 centimeters per second. But we know that when you make movements with the computer cursor, you aren't going really fast to the right and then really slowly to the left. In general, if you're going to the right, you're still going to the right. Does that make sense to everyone? Yeah. All right. And then we're also interested in things like nonlinearities, although we won't get to talk about them too much in the class. If you come to office hours, Professor Shenoy, Tushar, and myself will be happy to talk about those in more detail. And so in this lecture, what we'll do is we'll get into some modeling details that show us both how to fit the population vector, but then over the next two handouts, we'll also learn how to incorporate the spiking history, and then to take into account things like the inertia of the cursor. The reading for this lecture is held over from the previous lecture, and so we are just putting this reference here so you know where to go to in case you want more clarity on some of the topics in this lecture. This reference really does incorporate all the different decoders into one place and uses sort of the same notation. So, so if you're having trouble with any of the concepts, there's a good chance that this reference can help clarify some of those. All right. So when we showed you all the lab tour from 2003, I promised you guys a lab tour from 2014. And so this is what the Shenoy lab looks like just a year ago. And so we're going to zoom in on this video of the monkey, and let me just pause it right here. So this here is monkey J. Monkey J has, can someone tell me how many arrays are implanted into monkey J? Yeah, I see two arrays. So each box here is the buffer for one array. And so he has one array implanted into his motor cortex, M1, where we said there was movement, largely a lot of movement activity, and one array implanted into his dorsal premotor cortex. And the same hardware that we showed in the previous lecture is off the screen over here, where we had the same front-end amplifiers that are amplifying the signal and sending it through an optical fiber, if you guys remember, to our digital processors. So Monkey J is sitting very comfortably in this chair. And for Monkey J, both of his arms are sitting in these PVC pipes. And that's just to ensure that as he's doing this task, he isn't moving his arms. We wanted him for this task to completely sit still and control a cursor just by thinking about it. And so the cursor that he's controlling is shown on this monitor here. And when we zoom out, we'll see another view. But he's controlling the cursor to acquire some of the different targets. And so he's doing that, of course, just by thinking of it. And this is an example of what the motor prostheses in our lab looked like just a year ago. You'll see the control is pretty good. The cursor moves pretty directly to the target, and when it gets to the target, it's able to basically stop on the target to acquire it. And then these are the signals from Monkey J's 2 array. So this is his PMD array. And what we're looking at here is his M1 array. And so you'll see Monkey J's arrays at this point are 5 years old. And so even after 5 years, we're still getting great signals from him. And now they're 6 years old, and they still look like this. All right. Any questions on this? All right. All right, so I'm bringing back our block diagram that Professor Shenoy showed you from last lecture of our motor prosthesis, just as a reminder. So we'll have our electrode arrays. These are the Utah arrays that we talked about in handout 9, implanted into the motor cortex of our monkeys. We'll be recording these raw voltages, which, if you remember, will high-pass filter them to take away the slow-moving DC. And then we'll apply a threshold to detect the different spikes. Now, at this point, we could also apply our spike sorting algorithms, which will separate out the different spikes that might occur on every single electrode. But it turns out that for the data sets that you'll be working on in homework 4 and homework 5, and for most of the motor prostheses in the literature today, we actually just threshold the data without spike sorting it. And it turns out that that does well enough. Can anyone tell me why that might not do well? Why would it be bad to not spike sort? Brian?
If you don't spike sort, if you have a lot of artifact, you might not be able to tell the difference, right?
What kind of artifact are you referring to?
So you can have artifact from the needle, from the actual electrode itself, or you can have noise that just comes from a simulation.
Yeah, so there's a chance that noise could come through on top of the threshold, which could be misinterpreted as a spike. So that's one reason. Anjali?
Why doesn't it matter for this purpose if you're recording from multiple neurons?
Why doesn't spike sorting matter? Or I'll get to that. Before I get to that, though, can someone tell me why it might matter that that you don't spike sort?
When you don't spike sort and you're recording from multiple neurons, you can't differentiate them, right?
Exactly. Yeah, so if we were to, let me draw a picture. If we were to draw the tuning curve of a neuron, and here we show the reach direction on the x-axis, and the neuron's firing rate here on the y-axis. Let's say that we were recording 2 neurons on this electrode, and one neuron had a preferred direction at 180 degrees. And so I'll plop 180 degrees down here. And its tuning curve looked like this. And then we had another neuron whose preferred direction was 0 degrees. And so I'll put 0 degrees right here, and its tuning curve looked like this yellow curve. Now when these 2 neurons are firing, if they fire to, say, 0 degrees, we'll measure a firing rate that is the sum of those two. If you reach it to 180 degrees, we'll measure a firing rate, which is the sum of those two. And if you interpolate this, you would just get a flat line. And so even though you have 2 neurons, which are really very well modulated, because you're recording both of them and they're exactly anti-correlated, you've washed away any information on your electrode array, because all you're going to do is see a very high firing rate all the time. Does that make sense to everyone? So this is the extreme example of why not spike sorting could be very deleterious to your decoder. Now, this intuition definitely does hold. What we see empirically, and some of this is documented in some work from both our lab, but then also a lab out on the East Coast, Andy Schwartz's lab, it turns out that you don't run into this scenario that much. You do have multiple neurons on a given channel, but the performance that you achieve by just thresholding turns out to be just the same, or sometimes even better than with spike sorting. And then there are other reasons why this might come up. And so if you'll remember when we were recording action potentials, if this was just time, and we looked at the waveforms, and they're extracellular, so, they depolarize and then hyperpolarize. If we were to record this neuron over time, the electrode might slowly move further away from this neuron, or the neuron might move further away from the electrode, diminishing its amplitude. And it turns out that when its amplitude gets very low, you might ignore this spike because it doesn't look like a spike. It looks like quote unquote hash. But it turns out that this hash could be meaningful information from the neuron, and that hash could be modulated. And so there are reasons why this both improves performance and robustness, because we're still recording some of these very small signals that are meaningful for our decoder. And if you want to know more about this, there's a paper from our lab, which we'll put up on the readings page, by Chestik and colleagues in 2011. And I'll put that on the readings page. All right, so we detect our spikes, and then we'll pass them through a decode algorithm. And as you've been working on in homework 3, that could drive the communication prosthesis. So you've been working on classifying which target the monkey was planning to. Or it could decode an actual motor prosthesis. So this could be a robotic arm. Or what we'll focus on mainly in the next 2 lectures is a computer cursor on a screen. Any questions here? All right. All right, so I've plotted up this equation. Not to belabor it, you guys have seen this now 3 or 4 times. This is our population vector. And just as a reminder, we're taking the neuron's preferred direction, which in this case is pointing up and to the right. We're scaling it by the neuron's firing rate. And we're using that to decode kinematics, like the x and y velocity. And again, this looks just like a vector sum. And so if we were to just draw what the population vector looked like, what we could do is we could take our bin spike counts. These are the spiking signals from our electrode array. And what we would have is each neuron coming in and multiplying a preferred direction, as we see here, this neuron multiplying that preferred direction, and scaling that vector, that unit vector. And so if we were then to take all the unit vectors and sum them across, we would get our decoded velocity. And then from decoded velocity, it's easy to get the position out, right? All we have to do is integrate that velocity. And so if we were to decode the velocity of our neural prosthesis at time k, then we could get a position out by just saying the position in the x direction at time k is equal to what it was previously, plus our bin width times the velocity at time k. And so by decoding the velocities, we know all of our positions perfectly as well, because we can just integrate out those velocities to get position. That's how we actually put the position of the cursor on the screen. All right. Does that make sense to everyone? All right. So a second type of decoder is called the Wiener filter. And this Wiener filter is a decoder that we'll get to today. And many of you might have heard the name Norbert Wiener before. What this decoder translates into is using a history of neural data. And so each of these blocks, z minus 1, is a delay of 1 time bin. And so this is a canonical block that we use in digital processing. And so if the neural data here is yk, then the neural data here at this point would be yk minus 1. And for 2 of these z blocks, then the neural data here would be yk minus 2. And what we do in the Wiener filter is ultimately, what it can be reduced down to is we hit the neural data again by a vector of preferred directions. And so here, neuron 1 at time k will vote for its preferred direction. But then in this block, neuron 1 at just 1 time step earlier will also vote for a preferred direction given by the matrix L1. And so out of each of these preferred direction blocks, what we're going to get is a velocity based off of the neural data at time k, a velocity based off of the neural data at time k minus 1, a velocity based off of the neural data at time k minus 2, and then we'll sum all of those together to get an aggregate velocity. And so that's what the Wiener filter is doing. We'll also look into, in the next handout, Kalman filters. And so with the Kalman filters, what we'll do is we're going to have this model here called a kinematic dynamical model. And we'll get more into this in handout 13. But what this model is actually doing here is it's capturing the inertia of the cursor. And so if you can see there are these little arrows tying the x's through time. The x's are our kinematics, and the arrows tell us how the kinematics are related from one time bin to the next. And so with these kind of decoders, we can start to say, OK, the inertia of the cursor matters, or the dynamics of the robotic arm matter. And I want to incorporate those into my decode model. And so here's a video of the type of performance that we can achieve using these Kalman filters that have these state dynamical models over the kinematics. And so here, the monkey is, again, controlling this cursor with its neural activity exclusively. And you can see that this decoder is very, very good. It goes very straight to the cursor, to the target, excuse me. And when it gets to the target, it's able to stop and hold steadily on it. And so this is a study. The decoder here is called the refit Kalman filter. And it actually turns out that this improved the state of the art, which was something very close to what you saw in those videos that Professor Shenoy showed, by a factor of 2 times. And if you were to control this cursor with your hand, you would be faster than the refit Kalman filter, but the refit Kalman filter would get you 80 to 90% of the speed of the hand. So you would be able to acquire targets almost as quickly with the refit Kalman filter as you would with your hand. And then a decoder that we've shown here in the figure, but that we won't talk to too much, are decoders that are based off of more sophisticated machine learning techniques like recurrent neural networks. And so these networks are highly nonlinear, and you can think of them as very complicated interactions between hidden states. And what we can do is we can also decode with these nonlinear networks, and the performance of these decoders is also very good. And so here's an example of a nonlinear network that we built in 2012, and this is its decoding. So you can see that it also goes very directly to the cursor. Sometimes it overshoots, but when it gets there, it's able to hold on the target. And one of the benefits of these decoders is that because they're nonlinear, you can do a better job at reconstructing the underlying variables that you're decoding. And so one thing that we showed with this study is if you have the velocity of the monkey over time, or the speed of the monkey over time, when he reaches with his hand, the speed looks something like this. And so this sort of makes sense. The monkey, when he reaches to the target, will accelerate very quickly and then decelerate on the way to the target. And he'll reach really quickly. And so he'll have a pretty big acceleration. That's this first inflection over here, or this first increase over here, and a quick deceleration. And he reaches a peak speed somewhere in the middle of the trial. With the refit Kalman filter and other linear techniques, when we decode velocity, it looks something like this. And so he overall has a slower peak velocity, and he accelerates a bit more slowly, but he's able to, in the end, acquire the target at a similar time. And it turns out for these nonlinear decoders, since we're trying to reproduce velocity, decode velocity, these nonlinear decoders decode a velocity that looks something like this. And so they reach a higher peak speed, and they're able to accelerate and decelerate more quickly. And so you saw with this decoder that it went pretty quickly to the target, sometimes overshooting it. But part of that was it being able to reach the high velocities that the hand was able to reach. Does that make sense, Brian? Yeah.
Quick question. So the Kalman filter, please correct me if I'm wrong, does not require training, right? It just looks at the covariance and attempts to adjust itself based on what you see on observation, right? But on the neural network, you need to have a ton of training data. Mm-hmm. So in a real-time prosthesis, how do you sort of train the thing without the guy not losing functionality for a couple of minutes while you're doing that?
So good question. So for the Kalman filter, there is a training procedure. For all of these decoders, there's a training procedure. And we'll talk about how to train these decoders. So the covariance matrix that you mentioned is a matrix that we'll have to learn from training data. And so typically what we have for the videos that Professor Shenoy showed, and also if you remember that video of the woman with ALS who was typing on a keyboard from lecture 1, is where during that 10-minute block, we'll have them imagine moving their arm as the cursor is moving. So the cursor is going to move from the center to the right, then back to the center, from the center to the upright. And during those cursor movements, the participant is going to imagine moving their arm to the right and then back to the center, and then moving their arm to the upright and then back to the center. And those will constitute the training data that we use to either train our recurrent neural network or our refit Kalman filter. And it turns out that the amount of training data that we need to learn all of these decoders is about the same. Anjali?
With the recurrent neural network, is it easy to still have it reconstructing in real time, given that it's more complicated?
It is. So we can talk about this more offline, but the recurrent neural network has a very easy decoding equation. What takes long is the learning of the parameters. But after you know the parameters, it's actually very easy to decode. It's a matrix multiply and then a nonlinearity. All right, so the focus of these two handouts, this handout number 12 and then handout number 13, will be to how can we easily fit these decoders? And when I say easily, I mean we're going to do it in just a few lines of MATLAB. We're going to talk about Wiener filters, as we mentioned, that incorporate history in the neural data. We'll talk about these Kalman filters, which incorporate things like inertia or the dynamics of a robotic arm. However, to do so, we're going to need some tools along the way. And so these tools include linear algebra. And so why do we use linear algebra? Because it gives us a very easy way to consolidate and fit how many neurons relate to several kinematic variables. So if we had n neurons and m kinematics, so the m kinematics could be x and y position, x and y velocity. And we had n neurons, let's call it 100 neurons. So 100 neurons and 4 kinematic variables. This is 400 equations that relate each of the neurons to one of the kinematics. But with linear algebra, what we'll be able to do is we'll be able to write these 400 equations very easily as just one matrix equation that looks like this. So the activity of all the neurons at time k is equal to the activity of all the kinematics at time k through this matrix operation, through this matrix multiply. And then the other thing that we're going to have to talk about or learn about are noise models. And we won't delve very deeply into this. This will be mostly in Kalman filter land. But these noise models are going to allow us to weight neurons based on how reliable they are. And so this was related to one of the midterm questions where, if you remember, we had kinematics being decoded based off of 2 neurons. And they are neuron 1 and neuron 2. And neuron 1 fired at 25 spikes per second. And neuron 2 fired at 100 spikes per second. So which of these neurons is noisier? Neuron 1 or neuron 2? I see Richard. Yeah. Neuron 2 is noisier, and we know that because anyone know why? What do we know about the Fano factor of these neurons? It's 1. Yeah, so because the Fano factor is 1, the mean firing rate is proportional to the variance. And so neuron 2, because it fires at a mean firing rate of 100 spikes per second, will have a variance of 100 spikes per second. And so it's very variable, whereas neuron 1 will have a variance of just 25 spikes per second. And so because neuron 2 is a lot noisier than neuron 1, we'll want a way to automatically downweight neuron 2. We'll want this b to be smaller, or we'll want b to be small relative to a, because neuron 1 should provide more reliable, or will have more equivalent change in neuron 1's firing rate will have more information than that same change in neuron 2's firing rate, because neuron 2 is a lot noisier. Does that make sense to everyone? All right, so these noise models are going to basically measure how noisy these variables are. And automatically, they're going to adjust the weights of these coefficients based on how noisy they are. And so this is exactly what the Kalman filter does. And it's not just applicable in neuroscience, it's applicable in any problem where you're trying to infer a variable based off of many different sensor observations. And you want to know how to weight those different sensors because some sensors might be noisier than others. And so the Kalman filter is this very classical way for you to say, OK, well, I'm going to model the noise in each of these sensors. And based off of that modeled noise, the algorithm will automatically know to de-weight these more noisy sensors and to upweight these more reliable sensors. All right, and then before we actually delve into some math, we're just going to give a brief word on training and cross-validation. And so this is something that you've encountered in homework number 3 already, where for homework number 3, we asked you to create both a training data set, which had 100 trials per each direction, and a testing data set, which had 10 trials per direction. Does this sound familiar? Great. And so why do we do that? So in this lecture, we're going to start to train these decoders. But the way that we evaluate decoders is always on testing data sets. And why is that the case? Well, it turns out that this is a big topic in machine learning. Machine learning is concerned with both training and evaluating models. And so when we train our model, we use our training set. And that allows us to learn the parameters of the model. But we can't just go ahead and evaluate our model based off of how well we do on that training set. And the reason is as follows. So let's say that I had a neuron 1, and I was decoding x velocity. And let's say that these two things were linearly related in real life. So in real life, we have that Vx is equal to n1. But because we're also in real life, there's noise. And so let's just call that noise noise. And so if we were to then make observations of how n1 and Vx covary, we might get little dots that look like this. So in this case, when neuron 1 was firing at, say, 10 spikes per second, then Vx was, say, 5 centimeters per second. And so if we were to train a decoder, a linear decoder, we would do well to just draw a line that goes through all of these points. And we'll see that this line isn't perfect because there's noise, right? The line doesn't pass through each of these points exactly. But it models the data pretty well. Now, this is knowing that the model was linear. We could do this. But in general, we don't know what that model looks like. And so what we could have done is made this model more complicated. We could have said that Vx is equal to n1 to the 20, a times n1 to the 20, plus b times n1 to the 19, plus c times n1 to the 18. Some very nonlinear, very complex model. And if we were to fit this model right here, we might get a line that looks like this. And this would have 0 training error because this model passes through every single one of our training points. But then if we were to then look at a test data set of withheld data that we've never seen before, and that test data set looked like this. If we were to then use this really complicated model that we fit that looks like this, we would see that we actually wouldn't classify these points very well. And so by training on a training set and then evaluating on a testing set, what we're doing is we're making sure that our model generalizes to new data that it has not seen before. And this will prevent us from making really complicated, quote unquote, overfit models. So that's the terminology in machine learning, that you've overfit a model if you've made it far too complicated. Whereas in this scenario, the linear model, which the data were generated from, would do a lot better. Does that make sense to everyone? Any questions on that? OK. So in short, you always have to train your models on a training set. So those were the 100 trials per direction that you all generated on homework number 3. And then you'll want to test how well your model does on a separate testing data set. All right. So in the remaining 15 minutes, I'll want to go over an example of linear algebra. And so we know that for some of you who haven't had linear algebra, it's all OK, because linear algebra isn't a prerequisite for this class. We'll just go over some of the basic brief operations that we'll need to be able to fit these decoders. And so linear algebra provides a succinct way to deal with systems of equations. And so these are, we'll call the y's our outputs. These could be our neural data. We'll just call them outputs. And the x's here are our inputs. And let's say that we want to model these equations where y1 is are these coefficients times the various x1s, x2s to xn's. And the second output, y2, is also a linear combination of our inputs. Well, this is a typo. This should be x1. I actually took this slide from EE263, so they have a typo in their lecture notes. Yeah. And so it would be a linear combination of a coefficient times x1 plus a coefficient times x2, et cetera. And so the way that we can succinctly write these M equations is to write it as a matrix equation, y equals ax, where the y's are just the concatenation of all of our outputs, and the x's are the concatenation of all of our inputs. And then the way that this a times x works is that we're basically performing many dot products. And so a dot product is just if we have a matrix A11, A12 to A1n, and, well, it's hard to see, A1n, and we multiply it by a vector x1, x2 to xn. Then the dot product is just A11 times x1 plus A12 times x2 plus dot 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 A1n times xn. And so what we're doing in this matrix multiply is we're taking A11 times x1 plus A12 times x2 plus dot 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 A1n times xn. And this all equals y1. And then y2 will equal A21 times x1 plus A22 times x2, et cetera. Is anyone unclear on this? All right, so that's a basic simple matrix multiply. And so we'll just do an example because, one, this example will be useful again in the future when we look at Kalman filters. But also just to make it very clear how we model, for example, a kinematic update equation. So from high school physics, we know that we have Newtonian mechanics, and these are two equations that you probably used hundreds of times in high school physics. We know that the position at some time k plus 1 is equal to our position at time k plus the velocity at time k integrated out times delta t plus the acceleration twice integrated. And similarly, the velocity at time k plus 1 will equal the velocity at time k plus your integrated acceleration. And so the question is, how do we represent this with linear algebra? Well, the first thing that we want to do is we see that on the left-hand side of the equation, we have our kinematics at time k plus 1. And on the right-hand side of the equation, we have our kinematics at time k. And so what we want to do is ultimately we want to write an equation that updates the kinematics at k plus 1 as a function of the kinematics at time k. And so what we have to do is we have to first define what this vector x will be. And so there are, in these equations, basically 4 variables that are a function of time k. So there's the positions at time k, and so we'll just separate that into x and y position at time k. And then we have x and y velocity at time k. And then we're also going to put a constant here. And why do we have this constant? You'll see it'll be very useful for adding constants to our equation. And so if we go ahead and define this as our state, our goal is to write xk plus 1 is equal to a times xk. And so I put xk plus 1 over here. This is xk plus 1. And this is xk. So who wants to tell me what this first row might look like? Yeah. So it'll be a 1, right? Because pxk plus 1 is equal to pxk. So 1 will be here. And then there will be a 0 because pxk plus 1 is not dependent on py of k. And then to integrate out our velocity, vxk will be multiplying a term delta t. And then for this example, we'll just assume that a ball is dropping, so we only have acceleration due to gravity, and gravity only affects the y direction. And so and so we have this term 0, 0. And so this concretely, if we do the multiply of this vector times this vector, will give us pxk plus 1. That's this term right here, is equal to 1 times p of xk. So that's just p xk plus vk x delta t. Is that all clear to everyone? All right. So we can go ahead and write in that term exactly into our matrix here. For py, we now have this negative 9.81 over 2 times delta t squared corresponding to this term. And that's why we wanted our constant here, so that we could add constants to our equation. So this term here doesn't have any k dependence. But if we didn't have this 1 here, if this wasn't here, then we wouldn't have any way to add that. And so these 1s will prove useful in general when we perform these matrix multiplies. Similarly, we can go ahead and we can write out the matrix terms for the velocities in the x and the y direction. And so the velocity in the x direction will just equal the velocity that it previously was in the x direction because there's no acceleration in the x direction. And then the y velocity will equal the previous y velocity minus the integrated, plus the integrated acceleration, which is just that due to gravity. And then our last row is just a 1 because 1 is equal to 1 times 1. All right? OK, so given all of this, and we can go ahead and we can begin to start to build our motor prostheses. And so this is a slide that you guys have seen, that you all have seen now 2 times, where we have a monkey and he's reaching to different targets. And here we've shown both the plan activity and the movement activity. But for the rest of these slides, all we're going to have is movement activity. And so including in homeworks number 4 and 5, there will actually be even no planning activity in the data sets. The monkey will just be reaching to targets as they come up. And so there will be no green activity here. And what we'll be focusing on is the activity when his arm is actually moving. And so when he goes from this center target to this upright target, if we were to plot his position in the y direction, we would see that it goes up and then it holds up. And so here we have kinematic information. And then we also have equivalent neural information based off of the movement. And so when we perform a reaching task, when we have a monkey perform a reaching task, we have 2 sources of information which form our training set. The first is the kinematics. And this is the same from the example that we just saw. We have some vector x, which contains all of our variables of interest, the positions that we want to decode, the velocities that we want to decode, and a constant, because that'll be useful in the future. And then we'll simultaneously measure our neural activity, which is a vertical concatenation of all the neurons' firing rates. And so this will be the neuron 1's firing rate at time k, neuron 2's firing rate at time k, etc. And how do we estimate the neurons' firing rates? Sorry? Can you say it a bit louder? Thresholding gave us the spike trains. But then here we're not having a vector of just milliseconds with 1s or 0s based off of if it's spiked or not. But we actually want to get a measure of what its rate is, because remember from handout 7 and 8, we believe it's the rate that encodes information rather than the actual spike times. So does anyone remember how we get an estimate of the neuron's firing rate? Yep. Brian?
Do you just count the number of spikes and bin them?
Yeah, that's exactly it. So it's a very crude estimate of firing rate, but when we bin neural activity, and so let's say that this was our spike raster, and this, let's say, 50 milliseconds of activity. If we bin this into 25 milliseconds worth of activity, then we would count all the spikes in this bin and divide it by 25 milliseconds. And so that would give us the spikes per second, which is an estimate of the rate. And then we would go to this bin and then count the number of spikes and divide that by 25 milliseconds. And so the firing rate in this bin here, we would imagine would be higher than the firing rate in this bin here because this bin had 5 spikes in 25 milliseconds versus this one that had just 3. And so what we'll do is we'll bin our spike counts, and those bin spike counts are going to be our estimates of firing rate for the neuron Y. And what we'll want to do is we'll want to ask how, given these xk's and given these yk's across all time, remember k is indexing time, how can we build decoders from this data? Any questions on that? All right, so I'll leave off on this slide, and beginning next lecture, we'll actually learn how to fit these population vectors. But if you look at this population vector equation, you're going to see that there are a lot of numbers here that we would have to fit, right? We have the data that we observe. The data that we observe are the kinematics, x of k, and the neural data, y, k of I. And then we know n. N is the number of neurons, so we can cross out these n's. But then even after that, I have to learn what this c is. I have to learn these alpha i's, these bi's, and these di's, right? And how do we know what the preferred direction of a neuron is? Well, if you remember from homework 2, we found one way that we could interpolate firing rates with a cosine. So we could use that technique where we interpolate the firing rates with a cosine. But if we have n neurons, that means that we have to do this interpolation 100 times. And those 100 interpolations will give us these 100 vectors. But then we'll also have to compute these bi's, 100 of them, these alpha i's, 100 of them, and then this big c term that normalizes the entire thing. And so this seems pretty unwieldy to have to fit all of these parameters separately. And so when we return back on Friday, what we'll do is instead we'll write this equation as a simple matrix operation. And if we have just the kinematics as a function of L times Y, what that'll do to simplify this problem is allow us to just solve for this one variable L. Now, this one variable L inherently meshes all these coefficients together, but it's very easy to solve for this L using linear algebra machinery. And so what we're going to do is we're going to be able to write this equation as just one matrix operation. And then we're going to use linear algebra machinery to basically solve for L given our observations of the kinematic data, the xk's and the yk's. So the xk's are known. They're the kinematics that we observed. The yk's are known. They're the neural data that we observe. And so we have one unknown in this equation, which is just L. And so linear algebra will allow us to find that optimal L to decode neural data. All right, that's it for today.